Good morning. It's a pleasure to be here. And I would like to thank you for the invitation. So I would like to start by a little bit a vision. In the beginning of the millennium, you had three different fields of research: attosecond science, photoionization of atoms and molecules, and of course, quantum optics. Quite a disjointed field of research. 2010, part of this large field of research start to overlap, and photoionization became a very nice application of attosecond pulses. At the same time, you had beautiful experiments regarding entanglement and coherence in atomic and molecular systems. And the vision is that 2020, maybe there is an overlap between these three fields, and we start to be able to investigate quantum optics phenomena like entanglement in atomic and molecular system probe with attosecond pulses. And we are only beginning to do that. So this is a little bit this trajectory which I would like to tell you about. So a few words about the generation of attosecond light pulses. These pulses are generated when you expose a gas of atoms to a femtosecond intense laser pulse, and you get a train of attosecond pulses in the time domain, in the frequency domain. This is a spectrum of high order harmonics of the laser field. And of course, you can generate only one of these attosecond pulse. In the frequency domain, you have broad bandwidths. You can also, of course, generate just one harmonic and get a longer pulse. Or, and this is what I'm going to use in this talk, we can actually use this train of attosecond pulse and using the frequency comb of high order harmonics. Now, there are two conditions to generate attosecond light pulse. You need a strong laser atom interaction, which is well described by this very intuitive model where the electron tunnels through a potential barrier and then is driven by the laser field, come back, and leads to the, by recombination, to the emission of a short XUV pulse. And the second condition to have these pulses is that you need to achieve phase matching in this medium. And this is thanks to the presence of free electron in the medium that lead to this phase matching. Now, what I'm going to discuss mainly in this talk, that will be really all the time in this talk, is this process which is called laser-assisted photoionization, where you ionized an atom using combination of attosecond pulse train and a tracing field with a variable time delay. And this tracing field is often the field which is used to generate this attosecond pulse. And we look at the electron that are being produced in this process. And this is what I'm calling attosecond electron wave packets, because we have, of course, a broad bandwidth, and we generate temporally confined electron wave packets. So just to give you a picture of how such an experiment can look like, this is the case of a rather compact source, which we have in Lund. In these boxes, you have a laser. It can be a laser based on optical parametric pulse amplification, a few microjoule energy, 7 femtosecond pulse duration, 200 kilohertz repetition rates. It's in these three boxes. And then you have a vacuum equipment here in this first chamber, we generate these high-order harmonics or attosecond pulse. And in general, we have also an interferometer in order to produce this attosecond pulse in one arm and the dressing field in the other arm. And then we send this radiation into another chamber where we have some gas and where we detect the photoelectron. This was just to give you a little bit of picture what kind of experiments we are talking about. Let me come back to this scheme. And to introduce it, I would like to tell you how this scheme was first used to actually measure the attosecond pulses. And in this measurement, the assumption that is made is that the properties of this electron wave packet reflect very much the attosecond pulses, so that we can use what we measure here to deduce the property of the attosecond pulses. So to do that, we do interferometric measurement, and especially in the first implementation of this process, this was called Rabbitlike reconstruction of attosecond bursts, attosecond beating by interference of two photon transition. And let me explain to you what this technique is about. So we, as I said, we ionize a gas, and here is an energy spectrum using this high order harmonics. You have an energy spectrum here. We are in the XUV range, 80 to 100 eV, for example. In the time domain, this frequency COM here is a train of attosecond pulses. Now, if we just ionize with this frequency COM, we get electron at energies which are indicated here and which are separated by twice the laser frequency, which is used to generate the harmonics, because of symmetry reason, we only have odd order harmonics. And then now if we have a dressing field at frequency omega, this is the frequency picture of it, and now the time picture, then we can also have two photon transitions like indicated here, and we create sidebands in the photoelectron spectrum where we have absorption of this infrared radiation or emission of this radiation. So we generate sidebands. And the interesting part is that these sidebands can be reached by two quantum paths, and we have to add the amplitude of the two processes coherently. So we have here a quantum interferometer. And now we vary the time delay between our attosecond pulse train and the dressing field, and we are going to see oscillation of these sidebands. Now, this is a picture of the optical interferometer that we need in order to vary the time delay between the pulse train and the dressing field, and it's a Mach-Zehnder type of interferometer. We have the laser here, which is split into two. This is the pump arm, where the attosecond pulses or high-order harmonics are generated. And we filter out the fundamental field here. And this is the probe arm with a variable delay. Now, both radiation is focused into a vacuum chamber where we detect the electrons. And in the experiment I'm going to show you, we used a magnetic bottle type of spectrometer, and this is collaboration with Gothenburg University. The characteristic of this spectrometer is that we detect all the electrons. We don't do any angular resolution. We detect all of them independent of the emission angle. Now, this is a typical rabbit trace. So what is shown here is the photoelectron spectrum, energy versus the delay between the attosecond pulses and the infrared radiation. And you see indeed that this sideband oscillates very, very nicely. This is an interference equation. And now we can use the phase information, which is obtained from the analysis of this oscillation. And if we look now at our quantum interferometer, you see that the position of the interference is going to depend on the relative phase of the consecutive high order harmonic. And if we look at this phase, we divide by the actually energy difference between these two harmonics, we see that what we measure is actually an approximation to the derivative of the spectral phase, which is the group delay of our attosecond pulse. And this is how this technique was used in the first place and was invented in the first place, is to really measure the group delay of the attosecond pulses over a rather broad range of energy, as you can see in this example. This is a spectrum obtained in neon gas, where when the harmonics are generated in neon. And in this case, this leads to a pulse duration of 130 attosecond, which you get by simply taking the Fourier transform of the spectral amplitude, and we know the phase derivative, so we can take the Fourier transform and derive the temporal property. Now, as you can also see in this slide, the assumption that we are making here is that the ionization process is not affected the measurement, that this phase variation is mostly due to the properties of the attosecond pulse. But soon after that, it became clear that this process allows us not only to determine the property of the attosecond pulses, but also to study atomic photoionization. And this is the next part of this talk. Here we realize that, oh, but maybe we can get information on the photoionization process, but by the very same method, by the very same analysis, assuming, of course, that you know what is the influence of your excitation pulses. And there are two ways we have been doing that. The first way is to look at the influence of ionization over a broad spectral range. So for looking at non-resonant photoionization, and this is corresponding to a very short time scale, really in the attosecond range. And this is a story I'm not going to tell today. I really, you can look at literature regarding this aspect. What I'm going to focus on is actually resonant photoionization. For example, when you have the energy of one of these harmonic here corresponds to the position of a discrete state, and there is possibility for autoionization from the discrete state to the continuum. So by this very same technique, we can investigate photoionization. And the archetype of this process is phonoresonance. For example, phonoresonance in helium, and the most maybe prominent one is autoionization on the 2s2p doubly excited state in helium. This resonance is at 60 eV and can be reached by absorption of the 39th harmonic. So, and this doubly excited state can decay to the continuum P by autoionization. This process was in particular studied by Ugo Fano in 1961. And he really made a very elegant analysis, theoretical analysis of this autoionization process. And the interesting part here is this is quantum interference. You can ionize helium directly to from 1s to p, or via excitation to this state, which then decay by autoionization. And you have here a quantum interferometer. So Fano showed that he could describe this process with an amplitude factor here, which has a very simple form, Q plus epsilon divided by epsilon plus I, where Q is the asymmetry parameter, depends on the relative strengths between photoionization and excitation to the discrete state, and epsilon is the reduced energy, which depends on of course, the position of the resonance and the width of the resonance. So these are some of the cross-section that you can get depending on the value of the asymmetry parameter. You have a certain cross-section, but also a phase variation. There is a pi phase shift, which is associated to this going through the resonance. And although the variation of the cross-section have been shown since a long time ago using spectral lamps or synchrotron radiation, thanks to our attosecond technique, we could now measure the phase of this autoionization process. And the technique that we use is exactly what I have discussed. We ionize with another harmonic here, and then we have a dressing field leading to the formation of a sideband. And we look at the phase variation by looking at the oscillation of the sideband. And you see obviously that the phase variation here is going to be affected by the presence of a resonance. Now, this is an example of a result. So this is a rabbit trace, exactly as I showed you before. And here you have the integrated spectra. So this is the electron spectra integrated in delay. And here is the variation with delay of this spectrum. And indeed, you see again the oscillation of the sideband, but you also see, first of all, the imprint of the resonance on the harmonics. So very nice interference effect. And you also see, on looking at the sidebands, that we can see the influence of the resonance, and you can obviously see by eye that there is a difference in this phase variation of the sideband. Let me say that this result has been obtained by really working on the resolution of our experiment. We use a narrow probe bandwidth in order to increase the spectral resolution, and even a deconvolution algorithm in order to have a nice spectral resolution. So let's now analyze this phase variation, and this is what we do here. And so what I'm showing you is the amplitude and the phase. The experimental results are in blue, and the dashed line is just a fit, while the red line is the theoretical model using a Fano formula together with, of course, our experimental parameter. The discrepancy that you see at low photon energy is simply due to the spectrometer, so this is not so important. What you see is that first of all, there is a really strong interference effect. We almost go to zero here, and we see a very nice phase jump, which is not too far from the predicted pi phase jump. So very nice results. We can really retrieve with this technique the amplitude and phase through the Fano resonance. And using that, we can also use time frequency representation of this process. We can plot the Wigner distribution corresponding this process, which allows us to discuss the dynamics. This is the definition of the Wigner distribution. A is the amplitude. So you have both amplitude and phase here, of course. And what you see here is, so this is time on the vertical axis and energy on the horizontal axis. So we are in the femtosecond range here. The feature that you see at short time is the direct photoionization, while what you see at longer time is excitation to the discrete states that then auto-ionize. And of course, you have interference, especially a strong interference feature in the middle here, which corresponds to this interference minimum that we have seen before. So when we are here, we are very happy. But then we get the idea, oh, but what happens if we look not at the sideband 38, but at sideband 40? And so far we have been doing atomic physics a little bit like we are doing optics. We assume that we have a wave and we can determine the amplitude and phase and then do a Fourier transform, and we know the dynamics. Can we always do that? And we start to ask questions about the coherence. So let me illustrate this. What happens if we look at the sideband 40 instead? Well, we expect to see approximately the same result with, of course, the inverse phase, since we are looking in another arm of the interferometer. We see almost that, but not quite. As you see here, there is obviously a reduced coherence, looking at the interference pattern, a reduced contrast, and a reduced phase jump. So the question is why it looks like a loss of coherence of the electron wave packets. So what does it come from? And this loss of coherence can also be seen on the Wigner distribution, as you can see by comparing the two Wigner distributions. They are very, very similar, but there is really reduced interference phenomena on the sideband 40. So what is the reason for that? Well, looking a little bit at the spectrum of helium in this region, we see that around sideband 40, you have the 2p square state. So can this 2p square state be responsible for this apparent reduced coherence? And the answer is yes. By doing a theoretical model that now include the 2p square state, so it's more involved model, we can reproduce the reduce contrast and reduce phase jump in these results. So how can we interpret this now? Here is an interpretation. Now, if you look again at the spectrum, in two photon absorption, you can reach either continuum S or continuum D. And the 2p square only interacts with the continuum S, does not interact because of the angular momentum with the continuum D. So now if we look at the wave packet which is created in this sideband 40, there is the sum of two waves, an S wave and a D wave. So if this the angular, so we have we can write this using quantum mechanics language as a product of 2 degrees of freedom, the radial degree of freedom and the angular degree of freedom. If the radial part here can be factorized, then this wave function is separable. While if it's not, then it's like we have an entangled state. And in the measurement that we do an angular integration, which means that we trace over the angular degree of freedom. So by doing this, we average out this effect. So this looks like a loss of a coherence of the measurement. So our interpretation, again, it's an interpretation, is that this the fact that we have this 2p square resonance, which is very, very close to the energy of the sideband 40 and interact only with the epsilon S continuum, we have really a difference between the S wave and the D wave. And it's as we have, so we have an entangled wave function here, which since we are not looking at the angular part, we are not, we trace over it, and it looks like a loss of coherence in the measurements. So based on that, we would like to, we ask ourselves, oh, but can we characterize this attosecond electron wave packet in a better way and really measure not only the amplitude and phase? Does it make sense to measure that, but really measure the density matrix? So here I'm going to propose to you a method to do that. This is nothing we have done experimentally yet. We are building the setup at the moment, but this is just an idea that we propose to try to really characterize the quantum state of the wave packet that we state. And again, we use the same scheme, this laser-assisted photoionization, but now we instead of using this rabbit scheme, we propose this Kraken protocol. Kraken means poor guy in Swedish, and this is the it really means quantum tomography of attosecond electron wave packet. And here we create, so we are ionizing in the vicinity of a Fano resonance here using one harmonic, and we probe this harmonic using now two different wavelengths, and we vary not only the time delay this time, but also the energy difference between these two probe fields. And let me show the results of this protocol. These are just simulated data so far, but this is the prediction of these simulations. And I'm going to show you how we can characterize first a pure state. This is our 2s2p resonance in helium, or a mixed states, which is this time 3s-1 to 4p Fano resonance in argon. The reason we have a mixed state now is that because of the spin-orbit interaction, there is really an entangled state here between the state of the electron and the state of the ion. And since we do not measure the ion spin in our experiments, then again, we are going to trace over this, degree of freedom. And then we have mixed states with spin 1/2 or spin 3/2. And the protocol gives these results. This is now the density matrix in helium. So the diagonal is here. And you can see again the influence of this interference effect that you see very clearly in the density matrix. This is the amplitude and this is the phase. You have the phase jump here. Purity is very close to 1 in this case. And this is what we predict now in the case of argon. In that case, it's a much more complicated density matrix, and the corresponding purity is 0.68. So with that, I would like to conclude. I have tried to take you from attosecond pulses and the measurement of attosecond pulses using this laser-assisted photoionization process and this Rabbit technique. I have shown you how we can characterize resonant photoionization using this process. I have discussed a little bit some question we ask ourselves about the coherence and this electron wave packet that we created, and which led to this proposal of quantum state tomography protocol in order really to retrieve the real quantum state of this attosecond wave packet. And with that, I would like to thank my collaborators, especially David Busto and Hugo Laurel, for the last two results that I have shown you, the quantum state tomography and the analyzing of these helium results. And together with my other co-workers, collaboration with the group of Gothenburg University, and collaboration with actually many theorists, Luca Argenti, Fernando Martin, Andreas Büchleitner and his group, and Daniel Finkelstein Shapiro and Tony Pilerutz. Thank you for your attention.
Thanks a lot for the great talk, Anne. So now we have time for questions. Yes, please. We have a question here.
Yeah, thank you, Anne. Really great talk. You showed at the end how to evidence the difference between the two cases and try to evidence this entanglement. I was wondering what is exactly that you measure in the graph at the end when you show the density matrix. From your measurements with the two different frequencies, you directly get this density matrix. What is experimentally the signal you measure?
Yeah, first of all, let me stress that these are not experiments. This is theory. We are still building the setup, and we are so these are simulations. We measure the electrons again, but we measure. It's really, if I go back to this proposal here, we measure the electrons as a function of time delay, this between the dressing fields, which now is composed two frequencies, and the harmonic field, and as a function of the energy difference between the these two fields. And this allows us to really get the density matrix where you have epsilon and epsilon prime on both sides. So it allows us to get the coherences. With the Rabi technique, we only get the diagonal of this matrix, density matrix. But again, we haven't done that in the lab. This is going to be difficult, but we believe that this protocol should work. I mean, we have shown it in these simulations.
Thank you.
Okay, there seemed to be a question in the back, or so the question. This was a double question. So maybe I can ask you a very naive question. So you are working with this very high harmonics. So what is the main factor that limits you from going to even higher harmonics? And is there any sense in going to higher harmonics?
They are. We are working. Let's say typically we're working in the range 20 to 50 eV, sometimes around 100 eV. If you use mid-infrared radiation to generate the high harmonics, you can go to a few hundred of eV. So there is no fundamental limit, and of course, working to a higher and higher photon energy leads you into the X-ray range, which is of course very interesting for application, or soft X-ray range. And also, if you manage to get all of these harmonics in phase, you get even to shorter times, then you get to the attosecond regime, or at least a few attosecond regime. So that's the interest to go into this direction. There is no fundamental limit, but of course it's kind of difficult to get all of these frequencies in phase. I don't know if I answered the question.
Okay. Yes. I think more or less. Okay. Any other questions? I don't see. So let's thank Anne again.
Well, thank you.